Mars, a planet that once held flowing rivers and vast lakes, now stands as a desolate world, its secrets buried beneath layers of ancient rock. NASA's Perseverance rover has delivered the most remarkable footage yet, 4K visuals that reveal evidence of things we've never seen before. In this video, we're going to bring you face to face with the truth that's been there the entire time, just hidden from view. The rover's Our Eyes on Mars on August 6, 2012, NASA's Curiosity rover descended onto the dusty Martian surface in Gale Crater. This groundbreaking landing used the ambitious Sky Crane system, an innovative design that gently lowered the rover to the ground using cables after decelerating its fall with retro rockets. This method allowed for precise landing. In Gale Crater, a 154-kilometer wide basin rich in geological diversity, the site was specifically chosen because of the central Mount Sharp, a laid mountain potentially holding billions of years of Martian history in its sedimentary rock layers. Curiosity's primary mission was to answer one fundamental question: had Mars ever harbored environments that could support life? To accomplish this, the rover was fitted with a sophisticated suite of instruments, each serving a unique purpose. The ChemistryCam uses laser technology to vaporize small portions of rock and analyze their chemical composition from a distance of up to 7 meters. The MastCam, with its 2 camera systems, delivers detailed high-resolution images and stunning color panoramas, aiding in the selection of prime sites for further study. Another critical tool, the Sample Analysis at Mars Suite, made up of 3 instruments, working together to analyze gases, isotopes, and organic compounds in rock and atmospheric samples. Curiosity has made massive discoveries during its mission. It confirmed that Gale Crater once housed a lake system, supported by layers of mudstone containing clay minerals. These clays form in the presence of water, suggesting the crater had standing water for millions of years. The rover also detected fluctuations in methane levels in Mars' atmosphere, which, intriguingly, could have biological or geological origins. The presence of organic molecules found within rock samples hinted that Mars' ancient environment might have been conducive to life. These findings laid the groundwork for exploring deeper questions about Mars' habitability. But there was more to come. Perseverance, the scientist and sampler building on Curiosity's trailblazing success. The Perseverance rover embarked on a more daring mission, landing in Geological Crater on February 18, 2021. Unlike Gale Crater, Geological spans 49 kilometers and harbors a unique combination of features: an ancient river delta and a long-dried lakebed, rich in carbonates and clays. These materials are considered ideal for preserving biosignatures, making the site a prime candidate in the search for evidence of past microbial life on Mars. Perseverance's mission extends beyond mere exploration. Its objectives include the search for ancient life, the collection of Martian rock and soil samples for future Earth retain mission, and the testing of cutting-edge technologies to advance human exploration. Equipped with a sophisticated suite of instruments, Perseverance excels at conducting detailed investigations. Sherlock, mounted on its robotic arm, identifies organic molecules and minerals that may signify habitable environments, while PIXL produces high-resolution chemical maps of Martian rocks. Meanwhile, the MastCam Z camera system enables researchers to closely analyze distant targets with precise zoom capabilities. A groundbreaking addition to Perseverance's toolkit is the Ingenuity helicopter, the first device to achieve powered flight on another planet. On April 19, 2021, Ingenuity completed its inaugural flight, paving the way for aerial exploration. It continues to play a critical role in supporting Perseverance, scouting potential sites of interest and aiding navigation. Another game-changing innovation on board is MOXIE, which has successfully generated oxygen from Mars' carbon dioxide-dominant atmosphere, a vital step for future manned missions. Since its arrival, Perseverance has already achieved remarkable feats. It has collected multiple rock core samples, particularly from sediment-rich sites in the Delta region, likely deposited by flowing water billions of years ago. These samples could hold critical clues to Mars' ancient habitability and the potential for past life. These samples are carefully sealed, ready for a potential retrieval mission that will bring them back to Earth for detailed analysis. Innovation and exploration. Both Curiosity and Perseverance exemplify NASA's leap in autonomous navigation and mobility, allowing these rovers to traverse the unforgiving Martian surface with minimal guidance. Perseverance features the AutoNav system, a vast improvement over Curiosity's navigation. AutoNav processes terrain data in real time, enabling the rover to identify hazards and choose safer paths. This efficiency has dramatically increased the distances Perseverance can travel during its operations. Perseverance's ability to capture and transmit footage in 4K resolution also represents a technological leap. The visuals reveal Martian landscapes with an unparalleled level of detail, allowing scientists and the public alike to observe sand ripples, rock textures, and even the thin haze of the planet's dusty atmosphere. These images aren't just for show. They provide critical data to help geologists and astrobiologists pinpoint specific features worthy of deeper investigation. Curiosity paved the way for much of this success, offering vital lessons on everything from system durability to optimizing science objectives. For example, Curiosity's extended mission revealed that it could endure Martian winters and significant dust storms, which informed the design of Perseverance's reinforced hardware and energy systems. Together, Curiosity and Perseverance are achieving what was once only dreamed of, turning the distant red planet from an enigma into a site of groundbreaking discoveries. Through meticulous engineering, innovative technologies, and their sheer resilience, these rovers are rewriting what we know about Mars. They have bridged the gap between hypothesis and evidence, advancing our understanding of a planet that might once have mirrored Earth. NASA's Mars rover Perseverance has been sending back breathtaking footage, revealing Mars in unprecedented detail. Among its most notable achievements is the documentation of its descent and landing in Jezero crater on February 18, 2021. This event was captured through multiple cameras, providing an unparalleled look at the intricate landing process. In a groundbreaking first, NASA also released 4K resolution visuals of Mars, combining high-resolution images taken by the Curiosity, Spirit, and Opportunity rovers. Despite bandwidth constraints limiting direct HD video transmission from Mars, these visuals were meticulously stitched together from photos to provide a clear and stunning representation of the Martian surface. Perseverance's exploration of Jezero crater has uncovered ancient river delta formations, offering significant insights into Mars history. Its advanced imaging technology has allowed researchers to create detailed panoramas, shedding light on potential signs of past life. The Curiosity rover, though older, continues to contribute valuable data with its analysis of Gale crater's geology, complementing Perseverance's efforts. Together, these rovers enhance our understanding of Mars, creating a comprehensive picture of its past environments. These machines, working millions of kilometers away, bring us closer not only to the answers locked in Mars geology but also to the larger goal of exploring Mars as a future frontier for humankind. Revealing Mars' landscape, climate, and geological history. Mars' surface offers a rich tapestry of geological features, each with clues to the planet's dynamic past. Gale crater, Curiosity's exploration site, showcases an intriguing array of sedimentary rock layers within its central structure, Mount Sharp. These strata represent billions of years of Martian history, with each layer preserving details about the environmental conditions at the time of its formation. Scientists have identified signs of water-altered minerals, particularly clays and sulfates, which point to prolonged interactions with liquid water. Mount Sharp's towering slopes act like a time machine, providing an invaluable record of Mars' ancient wet periods transitioning into aridity. In comparison, Perseverance's exploration of Jezero crater centers around a river delta that once emptied into a long-gone lake. The delta's fan-shaped deposits of sediment are relics of flowing water that carried and deposited material over eons. These sediments include carbonates, materials known to preserve microscopic fossils on Earth. Detailed images from Perseverance reveal winding riverbeds and layered deposits, tangible signs that water not only existed but was stable for extended periods. Beyond these craters, Mars displays sweeping sand dunes, towering impact craters, and distinctive rock formations like the famed blueberries discovered by the Opportunity rover, tiny spherules formed by mineral-rich water. Wind erosion continues to sculpt the planet's landscape, creating rippling patterns of fine dust that evoke a dynamic system still active beneath Mars' quiet appearance. Mars has undergone dramatic climatic changes over its 4.5 billion year history. Early in its existence, Mars had a thicker atmosphere and supported large quantities of liquid water, as evidenced by sedimentary rock layers within craters and valley networks. Analysis of these layers by both rovers shows how minerals like clay formed in wet environments, further confirming the role water played in shaping the Martian landscape. Curiosity's findings in Gale crater indicate that lakes existed for millions of years, providing habitable conditions. Similarly, Perseverance's studies in Jezero crater highlight the delta and lake beds' potential to preserve organic molecules, crucial for understanding Mars' wetter epochs. However, Mars gradually transitioned into a cold, dry planet. This shift, largely driven by the loss of its magnetic field, allowed solar wind to strip away most of its atmosphere. This collapse exposed the planet's surface to harsh cosmic radiation and froze its remaining water into underground reservoirs or polar ice caps. Today, surface water exists only as briny trickles or sublimating frost remnants of a once thriving hydrological system. Mars' current atmosphere is 95% carbon dioxide, with a surface pressure less than 1% of Earth's, making it incapable of sustaining liquid water. Still, the planet's thin air holds valuable insights into its history. Isotope studies by Curiosity's SAM instrument reveal the preferential escape of lighter gases over billions of years, helping reconstruct the timeline of atmospheric loss. Seasonal variations in methane levels, detected by Curiosity and orbiting spacecraft, remain one of the most intriguing atmospheric phenomena. While methane can result from geological processes, it's sporadic and localized. Spikes raise questions about possible biological activity beneath the surface. Perseverance, with its advanced sensors, aims to follow up on these findings, offering additional clarity. Dust storms, another defining characteristic of Martian weather, can envelop the entire planet, reducing sunlight and temperatures. Perseverance and Curiosity's weather instruments have provided real-time data on these events, improving predictions for future missions. Observing these storms also reveals how wind shapes Mars' surface today, reminding us that, despite its ancient appearance, the planet remains geologically and atmospherically dynamic. Mars' diverse landscapes, from ancient river deltas in Jezero crater to layered sedimentary rocks in Mount Sharp, reveal a history shaped by liquid water. Geological evidence points to periods of lakes, rivers, and possibly even a more stable climate billions of years ago. Detailed analysis of clay and carbonate deposits shows environments that may have supported life. Atmospheric studies, such as tracking methane variations and the effects of dust storms, offer insights into Mars' transformation from a warmer, wetter world to its current arid state. Together, these findings reshape our understanding of Mars' potential to host life and similar processes on other planets. One step at a time. Did Mars support life? For decades, scientists have sought answers to the tantalizing question, did Mars ever harbor life? While no direct evidence has been found, intriguing signs continue to emerge. One of the most debated discoveries involves fossil-like structures embedded in ancient Martian rocks. Past rovers have captured detailed images of peculiar formations resembling microbial colonies, hinting at life's potential existence in Mars' wetter past. Further strengthening this possibility is the detection of organic molecules, carbon-based compounds fundamental to life. Curiosity's SAM instrument revealed complex organic chemicals preserved in 3-billion-year-old mudstone, evidence that prebiotic chemistry once occurred. Perseverance has taken this investigation further, using its Sherlock instrument to hunt for biosignatures, microscopic features within rocks that might signify past microbial activity. The methods and tools employed are strikingly similar to techniques used to identify fossilized life forms on Earth. Water has always been central to the search for life on Mars. Ancient hydrated minerals and water-formed clays, found in abundance at Gale and Jezero craters, prove that liquid water was present for millions of years in the planet's early history. Gale craters' sedimentary layers suggest a long-standing lake system, while Jezero's delta formations indicate a similar, water-rich environment, both of which could have supported microbial life. In more recent history, Mars water activity has diminished significantly, but not entirely. Subsurface radar mapping by orbiting satellites has detected vast quantities of water ice locked beneath the surface. Briny water, possibly flowing in underground pockets, offers a more intriguing prospect, one where microbial life, shielded from harmful radiation, might still exist. These findings continue to inform the rover's missions as they investigate areas where water may have left its mark.